Good day to everyone. Today we're going to discuss another method of solving systems of linear algebraic equations. So in this lecture, we're going to discuss Cramer's rule. So Cramer's rule is basically a method that uses the determinants of your coefficient matrix and a matrix that is obtained through replacing one column by a column vector of the right side of the equation or our variables or the constant values in our system. So in general, the linear systems wherein we will apply Cramer's rule will follow the form Ax equal to b. So given now several equations, they will all have the same form. So we have your Ax equal to. So according to Cramer's rule, the value of our variable x is determined by the ratio of the determinant of your derived matrix A divided by the determinant of your matrix of coefficients. So to understand this equation, we now define AI simply a new matrix that is formed by replacing now the ith column of our matrix A with the values of your column vector B. Okay. So for our derivation, to understand where this equation came from, let us consider now two equations with two unknowns. So given now e1x plus b1y equal to c1, which will now represent the first row of our matrix, and e2x plus b2y equal to c2, representing now the second row of our matrix. So in matrix form, that will now be e1, e2, representing the x column, b1, b2, representing our B column, Y column, and then we have C1, C2, representing our constant column or the C column. So to derive the equation for Cramer's rule, we have said we now have your two equations to unknown. So when we solve this algebraically, what we do is to solve for one variable by eliminating the other variables. In this case, I'll be solving for x by eliminating variable y. And we can attain that by multiplying equation 1 by b2 and equation 2 by b1. So simplifying, we'll now have a new equation. And as you can observe, b2, b1y is the same as b1, b2y in the second equation. Thus, we can eliminate y by subtraction. So, by subtracting equation 2 from equation 1, we'll now arrive at b2 a1x minus b1 a2x equal to c1 b2 minus c2 b1. So we could now solve for x as c1 b2 minus c2 b1 all over b2 a1 minus b1 a2. So from this equation, we can now write this in matrix form wherein c1 c2 is our first column for the numerator. Then we have b1 b2. Then for the denominator, we have e1 e2 b1 b2 as the columns. So if you're going to observe this equation now, for the denominator, and in matrix form, we could observe that e1 b2 minus b1 e2 is simply the determinant of this matrix. Okay? This matrix. So that is now the determinant of our given equation. One for our numerator, as you can observe, since we are solving for x, the variables in the x column is changed to the variables of your variables in or the values in our right side of the equation or our constant values. So to understand further, let us try solving for y by eliminating x. So we'll have the same process. We'll now be multiplying the first equation by a2, second equation by negative a1. So in that case, we'll now have a2 a1 x plus a2 b1 y equal to c1 a2 and negative a1 a2 x minus a1 b2 y equal to negative c2 a1. So we could now eliminate x by addition. So we'll now have a2 b1 y minus a1 b2 y equal to c1 a2 minus c2 a1. So y can be written using this equation or in matrix form. That will be a1 a2 c1 c2 denominator a1 a2 b1 b2. So again, we're going to observe the denominator will be the determinant of our variable coefficients, and for the numerator, so since we are solving for y, what we change is the column of y, which is b. We change the values of b into the values of our right side of the equation. Okay, so basically this will now be applicable for all variables in our equation. So Cramer's rule can be applied in any number of equations, and the number of equations should also be equal to the number of unknowns. So to understand Cramer's rule, let us solve an example. This example is a 2 by 2 linear system or 2 equation, 2 unknown. So given now the equations, let us solve for the values of the unknown variables. So we have 12x plus 3y equal to 15, 2x minus 3y equal to 13. So for our solution, let's write our system first into matrix form. We'll have 12, 3, 15, 12, negative 3, 13. So to solve this, we solve for the x value equal to the determinant of a matrix x and divide this by the determinant of the coefficient matrix. So same, y will now be equivalent to the determinant of matrix y divided by the determinant of our coefficient matrix. So with that, let us solve first our determinant of the matrix. So that's 12 times minus 3 minus 2 times 3, giving us a value of negative 42. So next, we solve for the determinant for matrix x. So this is our coefficient matrix. What we are solving is the values of x. So what we will do is to change or replace column x with the column of our constant. Okay, so with that, we can now solve for our determinant of x. That will now be 15 times negative 3 minus 13 times 3, giving us a value of negative 84. And then for y, So again, we have here our matrix of the coefficient. We are solving for the y column. So the y column now will be replaced by the coefficient of the constants. So dy now is equal to 12 times 13 minus 2 times 15, which is 126. So for dx, or for the value of x, that will now be 84 divided by 42, giving us a value of 2. And for y, that will now be 126 divided by negative 42, which is equal to negative 3. Okay, let's have another example. We have a 3 by 3 system. So we have 3 equations and 3 unknown x, y, z. So same pattern, we write our matrix form of the equations. So for this, we have 1, 1, negative 1, 6, 3, negative 2, 1, negative 5, 1, 3, negative 2, 40. So what we will need is x, y, and z. So basically, we will need our determinant of the coefficient matrix and the determinant of a matrix in which we have replaced the values of their column vectors. So for our determinant of the coefficient matrix, so we just apply Saru's method. So that will now be equivalent to negative 3. Then for x, given our coefficient matrix, we are solving for x. So what we will replace is the column of x. So that will now be equivalent to 6, negative 5, and 14. So solving, the x now is equal to negative 3. And then for y, so we will now be changing y with the y column with the coefficients of the constant column. So 6, negative 5, 14. So solving for the determinants, that will now be negative 5 times negative 2 plus 6 plus 3 times 14 times negative 1 minus negative 5 times negative 1 minus 14 minus negative 2 times 3 times 16. And this will give us a value of negative 9. And then for the determinant for z column, so we change the z column with the coefficients of the constant values. So solving for the determinant will now be able to solve for z equal to 6. So solving now for the value of x, that will be negative 3 divided by negative 3, that's 1. For y, that's negative 9 divided by negative 3. So y is equal to 3. And z is now equal to 6 divided by negative 3, which is equal to negative 2. So that's for Cramer's rule. So for Cramer's rule, again, this is applicable for any number of equations as long as the number of equations is the same with the number of unknowns. And in our solution, the determinant will be solved by changing the values of the column vector we are solving by the values of the coefficients of our constant column, or on the right side of the equation. So that's it for Cramer's rule. Thank you for listening.